doing NCERT exercise solution for chemical kinetics, and we will be doing 5 questions today, that is 4.1 to 4.5. So let us come to the very first question or the problem 4.1. In this, they have given that the rate expression of the different reactions are given, and we have to determine their order and the dimension of the rate constant. So the two things we have to find out. First is order of the reaction, and second is the dimensions of the rate constant. Okay. So let us have a look on the very first one. In the first reaction, rate is given as rate is equal to rate constant, and the concentration term is having a power 2. So therefore, we will write for the very first example, order of reaction is 2, because concentration term is raised to the power 2. Okay, and when we have to find out the dimensions of the rate constant, we will do it simply by rearranging the rate expression. So here the rate is given as K NO raised to the power 2. So rate constant can be written as rate divided by concentration of reactant raised to the power 2. Okay, now we will put down the units. Now dimension of the rate is moles per liter per second, and for your concentration we write in moles per liter, and we will put 2 here. So what will be getting the answer here? We will get it as, because this moles per liter will be cancelled by 1 moles per liter, so we are left with liter per mole per second. So this is for the first example. Now come to the second example. In the second example, have a look in the question. For this reaction, the rate expression is given as like this. For the first reactant, power is 1, and the second reactant power is again 1. Therefore, what we say, it is again the second order reaction. So order of reaction is again 2, and the dimensions of rate constant we will find out here. So we will write down rate as given in the question. Rate is written as K, concentration of hydrogen peroxide and iodide ion. So we will write it as concentration of H2O2 and concentration of iodide ion. So the K can be written as rate divided by concentration of H2O2 and concentration of iodide ion, and we will put down the dimensions or the unit here. So for rate, we write rate in moles per liter per second, and for first one, concentration is written as moles per liter and multiplied by moles per liter. This 1 moles per liter will cancel out, so we will be getting the same dimension, liter per mole per second. So this is the dimension of the second reaction, dimension of rate constant for the second reaction. Both the reactions are second order. So have a look here, dimensions are same in both the cases. Now come to the third example, and third example is this one. So have a look here, what is the rate expression? Rate expression is given this. There is only one reactant and the power of the reactant is 3/2. Therefore, order of the reaction will be order of reaction is given as 3 by 2. Whatever power we are having on the concentration term, that the same will be the order of the reaction. Now for calculating the dimensions of K, what they have given in the equation, rate is equal to K, and so we'll write it as rate is equal to K, concentration of CH3CHO, and raised to the power 3 by 2. So K, dimension of K can be calculated as rate divided by concentration of CH3CHO raised to the power 3 by 2. We will write it this in moles per liter per second, and the other one we will write in moles per liter, and we are keeping in bracket with the power 3 by 2. So on simplification, we will be getting here liter raised to the power half per mole half and per second. Okay, so this is for the third one. Order is this one, and the dimension of K is this. Now come to the fourth one, fourth example. So have a look here in the fourth example. In fourth example, rate is given by this. Ethyl chloride is there and the power is 1 only. So we will write down order of reaction is 1, and K is written as rate divided by concentration of C2H5Cl raised to the power 1. So rate is written in moles per liter per second divided by moles per liter. Moles per liter will cancel out, so we'll write with per second. And this is what we get dimensions of rate constant for first order reaction. So fourth example is a first order reaction. Now come to the second problem, and what they have given in the second problem, they have given a reaction 2A plus B is equal to A to B. Okay, so for this we'll write down the reaction. Reaction is given as 2A plus B is giving you A to B. For this, rate is given as rate is equal to K, concentration of A and concentration of B raised to the power 2. And value of rate constant is also given here. K is given as 2 into 10 to the power -6 mole per mole square liter square per second. Okay, this is the value of rate. So what we have to do in this question, you have to calculate the initial rate of the reaction when initial concentration of A and B are given, and calculate the rate of the reaction after A is reduced to 0.06 moles per liter. Okay, so we will first calculate the initial rate of the reaction. Okay, so initial rate of the reaction is given by the same term, and we will put down the values. Rate constant is given here. This is the value of rate constant, so it is 2.0 into 10 raised to the power -6 per mole square liter square per second. Okay, then we will write down concentration of the first one, which is 0.1 moles per liter, and we will write down for the second one, it is 0.2 moles per liter, and here we will put power 2. Okay, now when we simplify, have a look here at the units. These two will be cancelled by this because here again power is 2. So what we are left with after multiplication, value we will be getting as 8 into 10 raised to the power -9 moles per liter per second. Okay. So this will be the value of the initial rate. Now next they are asking that calculate the rate of the reaction after A is reduced to 0.06 mole. Okay. Now we will write down the condition here. So when A is reduced to 0.06 moles per liter. Okay, so what we have, therefore we can calculate amount of A reacted. Amount of A reacted will be, we can write it as originally what amount of A we are having, this is the original amount of A, therefore we write 0.1 as the original amount, and amount which is left is 0.06. So therefore amount of A reacted will be 0.04 moles per liter. This is the amount reacted. Therefore amount of B reacted will be what? Okay, now have a look here in the balanced chemical equation which is given to us. If 2 molecules of A are reacting, 1 molecule of B will react. Okay, so whatever amount of A will react, half amount of B will react to give the product. Or we can say if 1 mole of A is reacting, half mole of B will be reacting, or if 2 moles of A is reacting, 1 mole of B will be reacting. So accordingly what we will be doing here, therefore the B reacted will be half of the amount of A reacted, which is 1/2 into 0.04. So we will be getting it as 0.02 moles per liter. Okay, now therefore new concentration of B, new concentration of B will be, initially what amount we are having, initially we are having 0.2 moles per liter, so that is 0.2 moles minus amount reacted, we are having 0.02, so we will be getting 0.18 moles per liter. This is new concentration of B. So therefore new rate R dash will be written as why we are doing this, because we have to calculate new rate of the reaction, calculate rate of the reaction when these are the changes in A. So we will calculate new rate of the reaction, which is written as rate constant 2.0 into 10 raised to the power minus 6, and unit of kR per mole square liter square per second. Then we will multiply with the concentration of the first component. The first component, how much first component is left? A is left, this is the amount, and for B the amount which is left is this one. Okay, so we will be putting the value of first one 0.06 moles per liter, and for B we will be writing 0.18 moles per liter square. Okay, so again these unit will cancel out because we are having outside square, so these will cancel out, and on multiplication we will be getting the value as 3.89 into 10 raised to the power minus 9 moles per liter per second. Okay, because we are left with per second here and moles per liter here. So this is all about for the problem number 2. Now come to the third problem. In the third problem they have given the decomposition of ammonia on platinum surface, and they are saying that it is zero order reaction. Zero order reaction means rate is not affected by concentration of the reactant. So what they are asking, what are the rates of production of nitrogen and hydrogen if rate constant is given as this value. Okay, so before starting this, let us write down what is the equation for decomposition of ammonia. So ammonia, NH3, which is a gas, it undergo decomposition on platinum surface, and we are getting nitrogen gas plus hydrogen gas. And when we balance this equation, we write 2 here and we will be writing 3 here. So this is the balanced chemical equation for the reaction. And for this reaction, the value of rate constant is given, and it is this value. Okay. Now, according to the condition given, it is zero order. Therefore, rate is written as rate is equal to K concentration of ammonia raised to the power 0. Or we can write as rate is equal to rate constant. Okay, whatever is the value of rate constant, that will be the rate of the reaction. Why? Because this this part will be equal to 1. So now how we write rate of the reaction? Rate of the reaction can be written in terms of reactant as well as in terms of product. With the progress of reaction, concentration of reactant decreases and amount or concentration of product increases. So rate can be written as rate is equal to from this balanced equation, decrease in concentration of ammonia. And since here for in a balanced chemical equation we are writing 2, so therefore accordingly expression is written. Okay, and this is equal to increase in concentration of nitrogen. So we are writing plus sign here, and N2 divided by dt. Now again, which is equal to increase in concentration of second product, but here since the stoichiometric coefficient is 3, therefore we are writing 1 by 3, and then we are writing d concentration of H2 divided by dt. Okay, so rate can be written in terms of reactant and product in this way. So we have to remember this idea, that how we are taking in account the stoichiometric coefficients for writing the rate of the reaction. Now from all this, what we have general idea that all these rates, whether they are calculated in terms of reactant or product, they are equal to the rate constant, and for which value is already given in our question. Okay, so therefore rate of production of nitrogen, first nitrogen gas. Okay, the rate of production of nitrogen gas can be written as plus d N2 over dt. This is equal to rate constant, therefore this value is equal to whatever given, 2.5 into 10 raised to the power minus 4 moles per mole liter per second. Okay, now come to the second part, that is rate of production of hydrogen, rate of production of H2 gas. It can be written as plus dH2 divided by dt, and here we are multiplying rate with 3 into 2.5 into 10 raised to the power minus 4. This will give you the value of what you call rate of production of the other gas, that is hydrogen. Okay, why now question arises, why we are multiplying here 2.5 with 3. Okay, we have written, you can understand here separately, that rate is written as production of ammonia, which is equal to 1 by 3 d hydrogen over dt. This is in terms of, sorry, hydrogen. Okay, rate is written in this way. So here what we want, here we want this quantity, rate of production of hydrogen. Okay, rate of production of hydrogen will be 3 times the rate of the reaction, because what we will be doing here, we will cross multiply with this 3 and we will be getting this 3 here. Okay, so this is how we are getting the value, and when we multiply, we will be getting here answer as 7.5 into 10 raised to the power minus 4, and the unit will be per mole liter per second. So this is our answer. This is our answer, that is rate of production of hydrogen and rate of production of nitrogen. Now come to the fourth question. In the fourth question, they have given that the decomposition of dimethyl ether leads to the formation of methane, hydrogen and carbon monoxide, and the reaction rate is given by this expression. So first we write down the information. So rate is given as K CH3COCH3, that is dimethyl ether. This is written. Okay, so now the rate of the reaction is followed by an increase in pressure in closed vessel. So the rate can also be expressed in terms of partial pressure of dimethyl ether. And the new rate they have given in terms of partial pressure is this one. If pressure is measured in bar and time in minute, then what are the units of rate and rate constant? So what we have to find out? We have to find out unit of rate and the rate constant. Okay. Same expression can be written as rate is equal to K partial pressure of CH3OCH3, that is dimethyl ether, raised to the power 3 by 2. Okay. Now why we are doing? We can express your rate. In case of gases, we can express rate in terms of the partial pressure if the reaction is done at constant volume. And here we are doing in closed vessel. Okay, so therefore we will be using this expression for this reaction. Now rate is therefore written as, so rate can be written as minus D partial pressure of CH3OCH3 divided by dt. This is the rate of the reaction. This is equal to K, and it is written as partial pressure of CH3OCH3, and this is raised to the power 3 by 2. Okay, or it is better to write the whole quantity in square bracket. So we will write it as P CH3OCH3, and this is 3 by 2. Fine. So therefore dimensions of K. We will rearrange this equation. Here we can find out K if we take the other term, pressure term on the other side. So the dimension of K will be what? We will write in the numerator rate, and in the denominator this concentration term, which is partial pressure CH3OCH3 raised to the power 3 by 2. So therefore rate is written in bar per minute. As we see here, the partial pressure is written in bar and the change in time will be in per minute, and divided by your concentration term is in bar, and sorry, the partial pressure is given in bar, and we will be putting the power 3 by 2. So after simplification, we will be getting bar per half per minute. So our answer is dimension of K is this one. Okay. So unit of rate is, what is the unit of rate? From here we can write down here unit of rate from this expression, that unit of rate will be, your partial pressure is in bar and change in time is in minute, so bar per minute. This is first answer and the other one is second answer. And this is your rate. So next 4.5, and they are asking mention the factors that affect the rate of chemical reaction. So there are many factors. So number one, first is the which is most important, and all of us know it is a concentration of reactant. Okay, if whatever initial concentration of reactant we are taking, accordingly we will be getting rate of the reaction, and therefore we calculate the initial rate, because with the progress of reaction, rate of reaction changes, or rate will decrease if reactants are being consumed. Therefore, if we calculate initial rate of different reaction with different concentration of reactants, then rate will be affected by this. So first is concentration of reactant. Second one is nature of reactant and product. As you have seen in the previous example, if product are, or reactant and product are gases and the reaction is done constant volume, so in that case the rate can be expressed in terms of partial pressure also. And these if we go on accumulating the product, the rate of the reaction may slow down. So therefore, what is the nature of reactant and product, it will be affecting the rate of the reaction. Third one is temperature. You know that temperature and the kinetic energy of the molecule are directly related, and activation energy is also related to the kinetic energy. So the higher the temperature, higher will be the rate of the reaction, because molecules will be having higher kinetic energy and so higher activation energy. Fourth one is presence of catalyst. Catalysts are those entities which facilitate a low energy pathway so that reaction can be conducted easily and at moderate rate. Okay, so when catalyst is there, reaction can be done faster and it can be done at moderate value of temperature and pressure. Fifth one is surface area. Surface area of reactant. And it is found that as we increase the surface area, the rate of reaction increases, or reaction will be faster. Therefore, most of the time, the reactants which are solid, they are taken in the powdered form, because in powdered state, we have larger area and therefore reaction will be faster. And the last one is presence of radiation. Presence of radiation, and we can give very clearly here example of photochemical reaction or photosensitive reaction. The reactions where if we change if we expose the reactants to sunlight or ultraviolet light or a specific frequency wavelength radiation, then we can change the course of the reaction. Like for example, the halogenation in case of alkane, which is substitution reaction, it is initiated by the exposure of your halogen to the sunlight. Okay, or these are the photosensitive reaction. So this is all about for the factors that affect the rate of a chemical reaction. This is all for today.